Last time, I think probably everybody has a pretty good idea. That's one of the homework problems that you want to be capitalize on using that technique. And I think you also mentioned, if I recall, actually, in points 3 and 4. In the homework, I want you to use in points 3 or 4, those conditions. Yeah.
What is the homework?
Yeah, it was passed out on Tuesday.
You mean,
It's also on the web.
do you mean the not enough?
Yeah.
Blanks? Is that what you're talking
No, you don't want to constrain the ends. Okay, so it's not in conditions 1 or 2, but you have to use 3 or 4. All right, so you can look it up as far as those in conditions, saying, oh, do I know the gradient, don't I know the gradient, do I have to solve for the 2 points that make up the in conditions of the interval. So anyway, take a look. If you have any questions. All right, now we're going to start differentiation. There are 2 parts to this. The first is pretty evident to you, I think, as far as differentiation. If you've been through calculus and diff-EQ, you should not have a problem here. If you've made it this far, this will be kind of a no-brainer for you. The second part will be integration, and there are some very interesting algorithms that you use, but we'll go over that later. All right, simple rules for differentiation. I think these are pretty evident. You've got a calculus book or a math book of some sort somewhere. Let's see, if I remember, a couple of you use Maple, so it's actually literally a no-brainer if you're running Maple, but I think MATLAB can do these things too. So anyway, simple differentiation, providing n is not 0, just equal to dy dx is equal to nx, n to the minus 1. All right, and so if you substitute various values for y, then obviously you get these kinds of differentiation products. If y is equal to uv, then, okay, what's this called? Chain, right? Chain rule, okay. When y is equal to u over v, what do you get? Right. So pretty evident. Okay, now there are some terms that will come up every once in a while with regards to some jargon, principally in physics or the sciences or math. Sometimes they make it over into engineering, but not always. But I thought I would at least list these things for you. Special functions that are require an infinite series approximation. These are typically known as Sturm-Liouville equations. All right, these are the ones that you'll run into, and every once in a while you'll run into these things, right? Bessel functions, equations of this form. Now, what do I mean when I have a prime or a double prime?
First or second?
Yeah, first and second derivative, right? So Bessel functions. This is commonly found in fluids, or when we're dealing with waves, or even in heat conduction, and certainly in vibrations. Have some of you had the vibrations course with Doug Brown's? Okay, so you've run into Bessel functions. All right, Hermite equations, generally of this form. You find these principally in physics, more of the theoretical physics side, particularly in quantum mechanics. All right, Legere physics problems with equations of this form, and then Legendre, same as Bessel but spherical coordinates. Generally equations of this form. With regards to differentiation, obviously if you try to do this in thinking in terms of a computer and approximation, here's a delta x, so rise over run, right? That's the way you think of it. So what you want to do is the closer you get to the point that you're truly interested in, obviously the more accurate you're going to be. So if I go through a process of reducing the delta x, delta y, what series is that does that, right? That tells you if I shrink the delta x or delta y to 0, it's exact. What's that series called? Starts with a T. Taylor. Yeah, you'll see it in a minute. It comes back again and again. Obviously, in an analytical or exact approximation, if I had as delta x, delta y go to 0, I wind up getting basically the first derivative at that point. What is this, by the way? What's that called? Slope or tangent, right? All right, if I talk about integration, what is it that I'm really doing in integration? If this is a function, what is it that I'm doing?
Taking the area under the curve.
Yep, finding the area under the curve. How am I going to do that? I'm going to, ultimately, I will approximate it, right, with whatever intervals I will be using. There are all kinds of tricks of the trade to do that as accurately as you can. And we'll come back to that later. All right, comparison between differentiation and integration. Let's assume I'm dealing with a velocity here. So if I have y versus t, and I say, gee, I'm going to find the slope at a particular location, right there. How did I do that? The velocity, dy dt, right? Simple derivative. If I talk about integration, all right, so now I'm saying, I'm going to find what? The area under this curve. Right, so I'm coming down here, here's y versus t. That's equivalent to that value. All right, how did I do that? Well, y is the integral of the VTs, right? All the VTs along the line. Okay, now this one, you should have this down pat by now, right? Forward Taylor series. First derivative, second derivative. What would be the third derivative? It's not L. Can anybody say, what would be the third term?
F triple prime over 3 times.
Yep, that's it. That's how you do it, right? So you see the process just keeps going in. HOT, higher order terms. All right, so I can rewrite this in terms of the first derivative, right? So I just rearrange the equation, and I've got all this stuff left over. So all of that becomes the higher order terms, right? The largest of those higher order terms, of course, is that one, right? Because the other terms are smaller and smaller. Okay, so if I say, whoops, I just dropped that off. I'm just approximating that. To what order am I approximating that derivative? To what order?
The first order?
Yeah, why?
Because you only have one prime.
Because I've divided through by h, right? And so that's a first order approximation. First order, remember that, because sometimes I ask that on exams, yeah. H is the same as a delta x, or an interval, okay? You'll see this intermix. Some textbooks tend to use h, some use delta x, or they flip-flop back and forth. And I flip-flop back and forth, right? All right, we do backward Taylors, all right? You see kind of the same pattern, but all you have to remember is that the sign changes, right? Minus, plus, and so forth, right? So here's the approximation. First or second order? First order, all right? Central difference. Okay, what's going on here? I subtract the backward Taylor series from the forward Taylor series. You notice I now have I plus 1 and I minus 1 instead of I plus 1i or I and I minus 1. I plus 1, I minus 1. Right? So now I approximate this. Remember what this term was from the previous slide? It was a second order, or I mean a second derivative term, right? What is that? Third. Okay, so now what's the order of accuracy on this approximation?
So first order is divided by 3. Second order.
Anybody?
Second order.
Who votes for second order? Okay. Does that mean the rest of you vote for first order? No abstention. It's second order. Remember that. That one is very important. Circle that. If doing a central difference approximation, the order of accuracy is second order. And you can find that out yourself when you divide through, because you see you divide by h, you're going to have another h there, right? So anyway, second order. All right. If I want to do the second derivative, what's going on here? Here is a forward series, a backward series. I now add them, right? Now, why would I want to add them? What is it that I want to eliminate?
Every other term?
Well, look, if I want to know the first derivative, what do I want to eliminate up here? Yeah, I want to get rid of the second derivative and all those other terms. So all I want is the first derivative. So I do that by subtracting one from the other. I notice the sign change down here, right? So if I want the second derivative, what do I have to get rid of? The first derivatives. So if I add them, don't they automatically cancel? Right, so what I'm left with is this. So adding these two terms, I wind up with this expression. All right? This is a second derivative central difference. What's the order of accuracy of this?
Third.
Second. Anytime you do a central difference, it is second order accurate. Anytime you do a first derivative, one-sided difference, it's first order. All right? If you can. You always want to try to achieve the highest level of accuracy here with the minimum amount of work. It turns out that central differencing is probably optimal for a lot of numerical simulation. All right? Some examples of central differences. This is a simple first derivative central difference. All right? Now, what I showed you before was a one-sided difference, right? Because it was first order accurate. I minus 1 to I, or I plus 1 to I, right? Notice what it is here. I plus 1, I minus 1, divided now by 2, all right? What's the order of accuracy? Second. That's a central difference approximation of the first derivative. I strongly suggest that you be able to do that come first midterm. All right? That you know how to do that as a first derivative, and that you know how to do that as a second derivative. All right? I can go to a higher approximation on this by including more terms on either side of node I. All right? If I do so, you notice I have I plus 2, I plus 1, I minus 1, I minus 2. Right? Doing that kind of approximation, I'm now what order accuracy? 4. Right? So I've gained 2 orders of magnitude over this. Right? Here's the second derivative, second order accurate. If I expand it to 4th order accuracy, notice how many terms I have. All right? If I have a third derivative that shows up in the equation, like under the Stern-Liouville type equations, right? If I had a triple prime somewhere, that's what the approximation would look like if I did that third order.
How do you expand the second order to fourth order?
Yeah, what you're doing is adding and retaining more terms of the Taylor series, okay? That's how it works. Right? So it just gets a lot more algebra involved. Rarely do you use these or these. Probably hardly ever these, but every once in a while they might come up. 98% of the time you will use that approximation or that approximation. Okay? So circle those. Those are important. And you will find that you will need those later in other courses. All right, now this is called Richardson extrapolation. And this says, this is a little trick that turns out to be very, very effective. Now, what it means is if I take the derivative of whatever for that h, h2, let's say this h, remember, is like delta x's. So I run this for a certain interval. So let's say I start with H1, a coarse delta, right? And then I say, I'm going to run this again, and I'm going to have it, so I'm going to have twice as many deltas, right? So I'll cut it in half. So if I do that, and I extrapolate this thing, right, by just having that delta, there's some very interesting results that come out of this. It turns out that it's exceedingly accurate. And that's called a Richardson extrapolation. Okay, let's see what happens. I want to find the derivative at x equal to 1/2 using h1 equal 1/2 and h2 equal 1/4. All right, so why would I want to start shrinking down deltas, or the h's? Right, because remember Taylor's series. It says, as delta x or delta y, or whatever that delta is, as it goes to 0, what do you get? The exact expression, right? But we're approximating. So we know the deltas have that inherent error. That's called the truncation, or the HOT. All right, so let's see what happens here. Here's the function, right? So find D for H1. So here are the values. And what kind of difference am I using here? I'm solving for a first derivative, right?
Central difference.
That's a central. So I'm using a central difference, right? So I need the value at that point and the value there, right? So I plug those in. H is 0.5, so it's 2, so that would be 1, right? So I plug it in and I get a -1. The error on this is -9.6. Now I cut it in half and I do it again. But remember, in doing this, right, I have to go back to these. Now I -2, so forth and so on. I plug these values in, the same central difference. I get an error -2.4. All right, so this tells me that I'm going in the right direction by shrinking the delta x, or the h here, right, that I'm approaching. I'm getting a more accurate result. Now look what happens when I do extrapolation. I plug the value in here, I plug the value in here, run this little equation, voila. I just got an exact answer, right? So I did that by doing only 2 quick steps. Same procedure, I just cut the mesh, or the h value, the interval, in half. Extrapolated, got the right value. So I don't have to keep cutting these h's, you know, as I keep going down to try to get the exact value. All right, now, how did we do if we use a higher order form for the derivative? So remember, instead of a central difference, we're now doing an expansion that is 4th order accurate, right? So we've got a lot more terms. Okay, so we plug those values in, right? And we go, aha, so it's exact. So on something relatively simple like this, one explicit statement running at 4th order, right, would give me an exact value. Or I can do something at the 2nd order level, extrapolate. Okay, what do you think happens as we get to really large problems with lots of unknowns and so forth? Which method do you want to use? What do you think? You got to think like a computer now. You want to do the minimum amount of work, right? It turns out that if you go to these higher order approximations, it can actually be a lot more computational work versus doing more steps on simpler processes, okay? So that's what you have to juggle sometimes is, well, do I want to keep it simple but do a lot of them, or do I want to have this elaborate, elongated, highly accurate approximation? Gee, it's taking forever to get a solution, right? Okay, now, if I have unequally spaced data, so remember I assumed that the h's here were all the same, right? The value between I minus 1 and I, or I and I plus 1, whatever, were all the same. But if they're not, then this is the approximation that you have to use, okay? So now this accounts for the unequal spacing that you would have, all right, in data. And this happens a lot. So that's a general algorithm, basically. And obviously, it works very well. It collapses if the spacing is equal. But if it isn't, that's what you would use. All right? That's a 2nd order polynomial. Where does it come from? Lagrange interpolation. This is another form for unequally spaced data. Here, I have a first derivative, all right? And it's based over, it looks like a central difference approximation, right? I mean, in a way. What happens if the intervals are the same? That is, the xi plus 1 to xi, xi to xi minus 1. What does this collapse to? Yeah, what do we know? What happens? Well, if those intervals are the same, that's 1. That's 1. That value, that cancels. So I have f of xi plus 1 minus f of xi minus 1 divided by 2 delta x, or 2h, right? So it collapses to a central difference, second order accurate approximation, if the intervals are the same, all right? Same thing here for a second derivative, right? So if you program these things, if you set them up, you automatically have covered unequal spacing, but if it's the same as the intervals, it's automatically second order, right? Okay, let's assume we want to solve y double prime equal 2x plus 3y. Boundary conditions, y equals 0 is 0, y of 1 equal to 1, right? Let's assume we're going to use an interval h of 0.2, right? So I can write this in that recursion form or in finite difference form so that it looks like this. How did I go from here to here? What did I do? Okay. What do we know about this? That's what, first or second derivative? Okay. So I go down here and I go, I think that's a central difference approximation for a second derivative. And if you look at the little equation that we had, right, you'll see, oh, yeah, it is. Got it. That's the approximation for that second derivative using a central difference. So that's the equation that I'm going to solve. Now I'm going to solve this over all these intervals and stuff. So what I have, how many points do I have in this thing? Let's assume I'm running forward, right? So here's the little matrix that I get if I actually plug in values to this thing. So this is what the computer would be doing. What kind of matrix is this? How many diagonals? 3. So it's a tri-diagonal. If I solve for this thing implicitly, right, means I have to solve for the matrix. What algorithm would I use to solve this? Starts with an A, or starts with a T. Thomas. The Thomas algorithm solves these tri-diagonal matrices. That's what you use for cubic splines, right? That Thomas algorithm. Okay?
If you use Gauss elimination, is that the same answer?
You can use Gauss elimination, but in Gauss elimination, what's it going to waste its time on? All those zeros up there, right? And running a long Gauss elimination, a lot of code, versus a tri-diagonal, probably about 5 lines of code. Okay? That's the exact solution if you wanted to run that particular problem. Let's see how we do it. Okay, so here's what we get. Here's the comparison of the exact solution versus the numerical approximation and the values. All right, so how did we do? All right. Now, what? Remember, these are boundary conditions or endpoints that are set here. So those are fixed. So this is what we're looking at in the approximation of the second derivative. How well did we do versus the exact solution? Right here. And it's not too bad. You know, for engineers, that's okay. We can do all right. But in case you got a physicist type boss, He says, well, that's not accurate enough. What would you do? What would you do? You got two choices. Extrapolation, right? Or higher order approximation. But you're no longer tridiagonal, right? Because you have, oh, my matrix is now 5 diagonals instead of 3. I can't use the Thomas algorithm anymore. Now I have to use what? Gauss elimination, right? Unless I do an LU decomposition or something. That's going to take a lot more time. So the extrapolation, you use the same thing twice, probably a lot faster than going to a higher order. Okay, any question about differentiation? Right? It should be pretty much a no-brainer to you. The important thing to remember, the approximations using the Taylor series. First derivatives, second derivatives, first order, second order. How do you find the second order approximation? How do you set that up? What do you do? Add or subtract? All right? You start with a forward Taylor's and a backward Taylor's, and you're either going to subtract or add. Okay, if I want a second derivative, second order, central difference, I would add. If I want a second order first derivative, what would I do? That was not on the slides, but I want you to know if you can do that. So take a couple of minutes, do it right now, grab a partner. Let's be sure that you can do that. Okay? So you're going to do a second order first derivative approximation. Okay? Okay, next time we'll do integration, but just take a few minutes right now, grab a partner, let's see if you can do the first derivative. Okay.